Hello student, this is the third lecture on the ordinary differential equations. In this lecture we will solve the non-homogeneous linear differential equations. In the previous lecture we have solved homogeneous linear differential equation with constant coefficient. Okay, so today we are going to solve non-homogeneous linear differential equation with constant coefficient. In the first lecture we have defined what is the homogeneous and non-homogeneous linear differential equation of order n with constant coefficient. Okay. We are going to solution of non-homogeneous linear differential equation with constant coefficient. Of degree n. We know that the homogeneous linear differential equation with constant coefficient is of the form an dny over dxn plus an minus 1 nth minus 1 derivative of y with respect to x1 plus and so on. At last a1 dy over dx plus a naught y is equal to qx, where qx is the function of x. Non-homogeneous means on the right hand side we have a function of x. If this function of x we take it to 0, then this differential equation known as homogeneous. Okay, for non-homogeneous means here qx is not equal to 0. This equation can be written as in operator form an dn plus an minus 1 dn minus 1 plus and so on a1d plus a naught y is equal to qx. Here this is the operator and operate on y, where d is dy over dx. Okay. It is clear that this is the polynomial in D. Here an minus 1 up to a1 a naught, these all are constant. Okay, because we take here differential equation with constant coefficient. So here all coefficient of dn minus 1 d, okay, these all an minus 1 a1 a naught all are constant. Clear? So we can write this is the polynomial in D. Y is equal to qx, and suppose this is equation number 1. Here we find complementary function, and this denoted as yc of given differential equation 1. YC is the solution of YC here the solution of associated homogeneous differential equation to the given non-homogeneous differential equation. We take Q is 0, okay, then we have this differential equation equal to 0, this is the homogeneous, and here we call YC is the solution of homogeneous. If we take here 0, homogeneous linear differential equation, which we have solved in the previous lecture. Okay, so solution of an dny over dxn plus an minus 1 dn minus 1 dxn minus 1 plus and so on a1d plus, sorry, here we write in the form of derivative plus a naught y is equal to 0. This is actually homogeneous linear differential equation. Right hand side we take Q is 0. Taking Q is equal to 0 and we solve it, okay, and suppose the solution of this is denoted by YC, and this is called complementary function. So complementary function is the actually solution of the homogeneous linear differential equation associated non-homogeneous differential equation. And we find particular solution. And it is denoted by YB. YP is given by 1 upon PD QX, or this is actually 1 upon AN DN plus AN minus 1 DN minus 1 plus and so on A naught. We take here only operator PD, which is operate on dependent variable y, and this is actually operator, and this operate on QX. So this is known as particular solution of the given differential equation. Okay, here actually particular solution depend on the types of QX. Suppose we have QX is function of polynomial, okay, then we have a special method to solve to find the particular solution. And if we have QX is exponential form, e to the power ax or sin x cos x or log, then we have different cases to solve the particular integral for the given non-homogeneous differential equation. Okay, So actually here we try to find the solution of differential equation 1. So this is the process. First step, find the solution of homogeneous, non-homogeneous associated to the given differential equation, and suppose the solution is yc, and we also calculate yp defined by this, and this is yp is also a type of solution actually which does not contain any arbitrary constant. So it is clear. Then we have a non-homogeneous linear differential equation with constant coefficient. So first of all we find particular complementary functions, and second we find particular integral. Okay. Then solution of non-homogeneous linear differential equation with constant coefficient is given by y is equal to yc plus yp. This is the general solution, or we can say that this is the complete solution of the given non-homogeneous linear differential equation. So to find the solution of the non-homogeneous differential equation, first of all we find complementary functions and particular solution of the given differential equations. Okay, and particular solution is depend upon q. So we have the following cases to find the particular solution. Methods to find particular integral. We have following cases. Case first, if a right hand side of the differential equation, that is qx, is the polynomial in x of degree k. Okay, so direct we solve the sum questions related to this case. Okay, and we have some questions on this case. First question is, solve the differential equation. Differential equation is d square plus 2d plus 1 y is equal to x square plus 2x. So here actually right hand side is x square plus 2x. Here qx is x square plus 2x. Okay, so it is clear that given differential equation is non-homogeneous linear differential equation with constant coefficient. Okay, solution. First of all we find complementary solution. To find complementary solution, we make homogeneous linear differential equation to the given differential equation. Suppose this is 1, d square plus 2d plus 1 y equal to 0. Okay, taking here we take q is 0. This is the actually homogeneous linear differential equation which we have discussed in lecture number 2, solution of homogeneous linear differential equation. First of all, we find auxiliary equation, and auxiliary equation of this differential equation is just replace m in place of d and leave to the dependent variable y. Or this equation is m plus 1 whole square is 0. This implies that the roots of this equation are -1 and -1. Therefore, complementary function will be, here we have repeated root. So c1 plus c2 x e to the power -1 into x to the power 1 to the power minus x. Now we find a particular solution. Now, particular solution yp. Here yp is, we take operator here d square plus 2d plus 1. Okay, we take only operator part, not write y. Okay, into q is x square plus 2x. This is actually, this is operator. If the mean of this is integral of fx dx. Similarly, we have an operator which is of the type 1 upon d square plus 2d plus 1, which operate on the function x square plus 2x. So always keep in your mind, if qx is polynomial, right here, if qx is a polynomial, in x, and the degree of this polynomial is k, then we use binomial expansion. Okay, here x square plus 2x is a polynomial of degree 2. So we write here 1 plus something. So this will be actually like this, 1 plus d square plus 2d, because we use the binomial 1 plus x or 1 minus x to the power n or minus n. X square plus 2x. So we can write here the power of this is 1 and we take it on upside, then we have d square plus 2d whole power minus 1 x square plus 2x. Here actually we use the binomial formula 1. Here we have 1 plus something. Suppose this is 1 plus x to the power minus 1. So we use this formula 1 minus x plus x square minus x cube, and we have infinite number of the terms. If suppose that we have a binomial, then here we have all terms are positive and we have infinite number of terms here. Here actually we have a polynomial of degree 2, so we expand to this polynomial up to the power of d is 2, highest power of d is 2. So using binomial formula 1 plus x power minus 1, 1 minus x, and x is here d square plus 2d plus x square, and here x is d square plus 2d whole square. Okay, now next term is d square minus d square plus 2d whole cube. Okay, but we have to expand the binomial up to the power of d is 2. So next term contains the power of d greater than 2. Because we know that d means derivative of the function dy over dx of f of x. Okay, and we also know that if we take dn x to the power m, this is 0 when n is greater than m. So here actually power of polynomial is 2, sorry, the degree polynomial is 2, so the next term contains the power of d greater than 2. So when we operate to this operator on this function, then all terms will become 0. Why this fact? This is we multiply here simply. So this will be x square plus 2x minus d square plus 2d. This is an operator and operate on x square plus 2x. And from here just we take the terms of the power at most 2. So here we have a square plus b a plus b whole square. We have d d2 square means d to the power 4. So we can leave it, and v square means 4d square plus 2 times means 4 dq. So we can leave to the dq. We take only here x square plus 2x. X square plus 2x, and all terms will become 0 because next we have the terms containing the power of d is greater than or equal to 3. Okay, x square plus 2x. Now we operate d square. D square means 2 times derivative with respect to x. 2 times derivative of x square 2, 2x 0. Now we operate 2d. d means derivative of x square, 2x, 2 to the 4x, and derivative of x, this become 1, and 2 to 4. Similarly here we have 4 times 2, all terms become 0. So we have x square plus 2x minus 4x plus 6 plus 8. Solving, we have x square minus 2x, and from here we have minus 6 plus 8 plus 2. Therefore particular solution, this is actually particular solution for the given differential equation. Yp is x square plus 2x minus 2x plus 2. Hence complete solution of given differential equation is y is equal to yc plus yp, and yc is c1 c2 x e to the power minus x, and yp is x square minus 2x plus 2. So this is the final solution of the given differential equation. Next question on this method. Solve to the differential equation d square minus 4 y is equal to x square. So first of all we find complementary function. In short, we can write CF, and it is denoted as YC. Okay. To find it, we just take m in place of t, and we have m square minus 4 and take it 0. From here we have roots of this equation plus minus 2. So we have two distinct roots. Therefore the complementary function of the given differential equation c1 e to the power 2x c2 e to the power minus 2x. Now we find yp. Yp is equal to 1 upon operator is here d square minus 4 into x square. Okay. So first of all we write to the denominator like 1 plus something, so we can take here minus 4 is common, Here we have 1 minus d square by 4 x square. Okay, this is minus 1 by 4, 1 minus d square by 4 power minus 1 of x square. Here we can easily use the binomial expansion, and we extend expansion up to the highest power of d is 2, because we have here a polynomial of degree 2. One plus d square by 4 plus d to the power, here actually we have in both place minus and here minus, so all terms in the binomial expansion are positive. 16 plus and so on, x square minus 1 by 4 x square plus d square by 4 x square, all terms will be 0. 4x square, and derivative of this with respect to x 2 times 2x, and the derivative of 2x is d square x square is 2. Upon 4. So this is actually x square plus 1 by 2. This is the particular integral, particular solution of the given differential equation. Therefore, yp is minus 1 by 4 x square plus 1 by 2. Hence, solution of given differential equation y is equal to yc plus yp, and yc is here c1 e to the power 2x plus c2 e to the power minus 2x, and yp is minus 1 by 4 x square 1 by 2. This is the complete solution. Next question. Question is solve to the differential equation. Differential equation is d square y over dx square minus 2 dy over dx minus 3y is equal to 5. Here a right hand side of differential equation is a constant. Constant is also polynomial of degree 0. Okay, so if we have like this, yp is equal to an dn plus and so on a naught, and here we have some constant v. So direct you can write this will be minus v upon a naught. Okay, here you have to take only, here a naught is -3, so here the particular solution will be 5 upon -3. Okay, this is true when here q is constant. If q x is v some constant, so first of all we find complementary function. To find complementary function, we find auxiliary equation m square minus 2m minus 3 is equal to 0, and root of this quadratic equation, m product is -3 and sum is 2, so we can take 3 and -1, sum is 2 and product is -3, 1 and m 3 is equal to 0. This is the factor, so we can take root of this differential equation -3, -1 and 3. Therefore complementary function c1 e to the power minus x plus c2 e to the power 3x. Okay, now particular integral, this will be d square minus 2d minus 3, and here we have only 5. Okay, so the here actually you take a common -3 and take it to upside, so we have 1 plus something whole power -1. Okay, so there is a constant, so we take only first term, or we can write direct minus of -3, so this is 5 upon 3. Let me check the answer of this question. Actually here is only, there is plus. Okay, therefore solution of the differential equation yc plus yp, and yc is c1 e to the power minus x plus c2 e to the power 3x, and p is minus 5 upon 3. This is the complete solution of the given differential equations. Okay, so if we have a polynomial or constant, then the process is same to solve these questions, or you can solve this like that. You don't need to write here direct. You can also use the same process here. This is -1, and here we have -1 by 3 d square 2d whole power -1 into 5. Okay, because this is the polynomial of degree 0, so we can take only first term, because when we operate 5 on this, the derivative of constant is 0. Okay, so this is 3 pi plus all terms are 0. This is pi by 3. Hence solution of given differential equation y is equal to yc plus yp. Yc is c1 e to the power minus x, c2 e to the power 3x plus yp. Yp is minus 5 upon 3. So similarly we can solve some problem on this. If we have q is polynomial of degree k. Okay, in the next lecture we will solve the homogeneous differential equation, non-homogeneous differential equation, when qx is the function of or in the form of exponential. Okay, when qx is exponential function. Okay, thank you.